Hi class, this lecture is going to be about density and this is chapter 2.7. So bone density, this is a good example of density. Density, very simply stated, is how dense something is made up from. So if there's a lot of molecules pushed together, the substance is going to be really dense. If the molecules are not and they have more space, there's more room for these molecules, atoms, whatever the makeup composition is, to be more spread apart. So there's not as many packed in. So here's pictures of one of bone density analysis. Normal bone here, bone with osteoporosis is B. You can see that the bone in A is really solid, and how they test this is with bones with high density will block more of the x-rays compared to bones that are less dense. So looking at the x-rays, A, the bone density is really more solid. It doesn't look like there's a lot of pretty much decaying. If you look at it this way, this one looks like it's pretty much kind of just withering away. I know these are not technical terms, but you understand the big difference visually looking at these. That the person that has the osteoporosis might have some problems if they fall by breaking their bones, and even worse. Where somebody with a normal bone, with this being solid, the x-rays are not going to be able to go through, and that's a good thing. You want to keep your bones as solid as possible. This is bone density. They check this. So how dense something is, in this case, the denser the bone is, the better. So density is a ratio of an object's mass and its volume. Simply stated again, how dense something is. If you hold styrofoam is a very low density material. So even holding huge amounts of styrofoam, really not going to weigh you down because of the fact that it's just a low density material. The molecules in it don't have much mass, and there's a lot of space in between them. However, if you hold something like a brick is way more dense, and that's because the molecules have just been shoved together, if you want to think of it, very, very dense. So they are packed more closely, so there's going to be mass behind it where the styrofoam does not have it. So when you think of density and how dense something is, a brick has a very large amount of density to it. Everything's dense in it, where styrofoam, low density material. These two items may be the same size, but they do not have the same mass, because the closer the atoms or molecules are more closely packed together in an object, the greater the mass. So think of it this way. You have two elevators. One elevator has very few people in it. They space out. So if you had to look at the mass of everybody in the elevator plus the elevator, it's not going to be as much as compared to an elevator just jam-packed with people. They're shoving people in. That's way denser. Not a lot of space in between each person, that's being shoved in there. You can see just kind of a visual here. So even if these are the same size, they will not be the same mass. Density the density of a substance depends on the type and strength of bonding and how atoms and ions are arranged. Heavier density substances like metals are dense because the atoms are tightly packed together. Substances with simple molecular structures have lower densities. The weak forces between them, between the molecules, cannot pull the molecules together tightly. So there's more air, there's more space, and that makes it a lighter density material. Density can determine whether an object will float. If an object is less dense than a liquid, it will float. If an object is more dense, it will sink. Perfect example is a ping pong that floats on water. The density of a ping pong is a very low density material, and it means that when we put values to these, and everything has a density value, that means that because it's not sinking in water, it's got a numerical value that is actually smaller than water, or if you think of it in terms as lighter than water. So it's going to stay on top. It's no matter how much you push it down, it's always going to come back on top because it's not as dense as water. Here, if you look at these pictures, anything that's got a very high numerical value is really dense, which means if you feel it, you're going to feel the heaviness with it. It's just going to sink. Why? Because water is 1.00 grams per milliliter. Anything higher than this numerical value is going to just sink. Anything above or smaller than is just going to float on top. And if anything's close to it, it's going to kind of stay in the middle. So you see ice is very close. So you see it's not sitting on top, but it's not at the bottom. It's going to stay somewhere in the middle. The density compares the mass of an object to its volume. So the formula is density is mass of a substance over volume of a substance. And the units are either grams over centimeters cubed or grams over milliliters. Now remember, centimeters cubed and milliliters are interchangeable. They are equal to each other. Density of gas is usually grams over liters, and we'll cover that later in another chapter. So give an idea, let's go through these exercises to help you understand density. Objects A and B have the same volume, but A has a greater mass. So which is denser? This goes back to the styrofoam and the brick. They can have the same volume, but the brick is always going to have a greater mass. So if you said same volume, different masses, A has more mass per volume. So it's more condensed with molecules shoved together than B. Objects C and D have the same mass, but C is larger. Which is denser? So same mass, but different volumes. Object D has more mass per unit volume. Density, because density is an intensive property, it is independent of the size of the sample. Does not depend on the amount of matter. I'm not sure, I don't think your book talks about intensive property. I'll have to check again. But I'm letting you know that this is a term that density for materials, it's like a fingerprint. If you wanted to know what a material is, you could check the density of it. That density goes with that material. It doesn't change no matter what the size is or what the sample is. If you look into the makeup of it, it's always going to be this numerical value regardless. Pure water is always going to be 1.00 grams per mils, no matter where it's at. That's just what the makeup is. So you don't need a lot of it to know that it's still water. You can have a pool of it, you can have a drop. It's still going to have the same numerical value if the conditions match and so forth, and it's pure. A large piece of aluminum and a small piece of aluminum have different masses and volumes, but the same density. So regardless of the size, if it's aluminum, they're going to have the same density. So we use this to identify substances. Think of it as a fingerprint for aluminum. That it will always have the fingerprint for aluminum. It will not have something else. Here is a list of densities for some common substances. So you can see here they have body fat, cork, ice, muscle, sugar. I had one chart that even had strawberries. This one does not have strawberries on it. See, liquids, density, urine. There's different densities for everything. People study all this stuff. And you can see the units, grams per mil. So densities, let's get into calculations. You first need to make sure you thoroughly understand the formula for density. Density equals mass of a substance over volume of that substance. So you need to know units. And one of the biggest things that students struggle with formulas is they get lost right away. Understanding units and you just have to make an effort. You have to write this down. You have to memorize it. Density is mass. Mass is grams. In this case, right now it's grams. And volume is either going to be centimeters cubed or mils. These should always go hand in hand. So if you are given a problem, look at what the units are. The units will usually tell you what you're given and what you need still. So calculate the mass of 41.0 mils of mercury. The density of mercury is 13.53. This is a perfect example. This is giving you, it wants the mass, so it wants this one, but it's giving you the volume and it's giving you the density. So I jumped straight to a problem that we can rearrange this formula, and we'll rearrange this formula a lot in this class. So you need to understand that it's not just a straight way of determining density. We can determine mass and we can determine volume, which we will. So we rearrange this to solve for mass. So that means that volume times density is going to equal mass. How do I know that? Understand units. If you understand the units that go with density, you can use 99% of the time, you will not get the problem wrong. Write out volume, write out the units for volume, write out the units for density. Density, the mils will cancel out. This leaves us with grams. So now that you know what the formula is, plug everything in. We have 41.0 mils, and we set up the density. You don't need to write 1 here, but if you're having problems understanding, write 1. And then the mils will cancel out, and this is going to give us 555 grams. This is 3 sig figs. Remember, we never use the 1. If we were looking at sig figs, we would use this top one, but since this is 3 figs, it overrides it anyways. Determine the density for a 20 ml sample of a salt solution that has a mass of 24 grams. This is a very straightforward of just determining the density. It's saying it right here. So we plug in what would be for mass, we plug in what would be for volume, and we set up 24 grams over 20 mils. Make sure you carry these units. These units do not cancel out, so you need to carry them over. This ends up being, why does it say 2 sig figs here? And there's 3. This is an error. This should be 3 sig figs. So 1.20 grams. I need to fix that on the describing the slides. So again, set up the mass, the volume, and then divide by into each other, 20 into 24, and the result will be 1.20 grams per ml. 3 sig figs, not 2. So we're going to expand on density, but it's going to be about volume displacement. Volume displacement is really simple to understand. Have you ever gotten into a bath filled with water and you get in and water spills out? That is volume displacement. The density, the amount of density, let me explain it this way. Water spills out when you get in. If you catch that water increase, then you will be able to determine the volume that you just displaced that water. So let me see if I can explain a little better. Here we have a volume of water, and it's known at 35.5. We add this cylinder into the water. That pushes the water volume up. Why? Because this displaced the amount of water that was at 35.5. So knowing what the water displacement is, we now know the volume of the substance, in this case, the cylinder. Same thing as a person going into a bath. If we know the volume of the bath before the person goes in, and we catch all the water that is displaced, we now know the volume of that person. So we're going to use, this is a good thing to use for substances that can't be monitored or measured in the same way as other items that would be easily to determine what the volume is. So this is volume difference, or volume displacement. The density of a solid zinc object is calculated by dividing its mass by its displaced volume, not the volume, but its displacement. To determine its displaced volume, submerge the solid in water so it displaces water that is equal to its own volume. So here it's just we have to do an additional step. We need to know the volume that was displaced. So we have the mass of the zinc. In this picture here, this is a balance. If you were in person, you would be very comfortable using this balance by the time the semester ended. And it's pretty much a scale. That's all it is. It's in grams. It goes in this, and for this picture, it goes up to the hundreds. We place it in here, mass of zinc object. It tells us this is 68.60 grams. So we have our mass. We now need our volume for this zinc object. So here's our formula. Density equals mass. We have the mass filled out, and we have a volume here of 9.5 centimeters cubed. Now let's see how that was figured out. So again, we look at this picture. We started out with 35.5. We added the cylinder in. It resulted in 45.0 mils. Simple is subtraction. We take the final volume minus the initial volume, and that gives us the volume of the metal, which is 9.5. Now, we're dealing with a solid, so we don't want to deal with mils. Your problem should always specify, and will specify, what the answer or the unit should be in. And remember, these are interchangeable. So we want to change it to centimeters cubed for a solid. So follow the subtraction and addition rules, because they're not the same as multiplication. So we're going to figure out what the, the multiplication, subtraction rules are. So this ends up being 9.5 centimeters cubed. Set this on the bottom in the denominator. Now we will follow multiplication and division rules. And this ends up being 7.2 grams per centimeter cubed. You have to bring the units over. And since this is two sig figs, and multiplication and division rules are different, they want the value with the lowest amount of sig figs. This is what our answer is. So when we're doing volume displacement, you should have an initial volume, a final volume, and you subtract those, and that gives you the volume of the item you're interested in. Here's another one. What is the density of a 48-gram sample of a metal if the level of water in a graduated cylinder rises from 25 mils to 33. So here we have a 48 gram sample. That's our mass. We need to know the volume. And we get the volume by looking at the differences in the volume when the volume was raised with the metal in it. Remember, it's final minus initial, and that will give us our volume. So we have 33.0 mils minus 25.0 mils, and that ends up producing 8.0 mils following the subtraction rules. We will now plug that in for volume on the bottom, and this gives us 6.0 grams per mil. This is the density of the metal of a metal. Now it's asking for, it didn't say what units it wanted it in. Oh, it says it here. I added this, so this is my mistake. It wants it in mils, doesn't matter. Mils and centimeters cubed are the same. Unless it's specifying that it wanted it in certain units like it did here, and I messed this up. This is my mistake. Make sure you always pay attention if it is, and put it in mils. But your book left it in grams per mils, so we're going to leave it in grams per mil. And that's it.